Sketch the graph of the function f of x equals x divided by x squared minus 4 by determining the parts a through I. F of x equals x, a polynomial term, the domain will be all real numbers, divided by x squared minus 4. So f of x has a denominator. The denominator can be factored here. It is a difference of squares, so it'll factor into x plus 2 times x minus 2. And the domain requires that the denominator cannot equal to 0. So x plus 2 times x minus 2 cannot equal to 0 here. Since it is factored, we can solve for the values that x cannot be. The x plus 2 factor gives that x cannot be a negative 2, and the x minus 2 factor gives that x cannot equal positive 2. So for part A, the domain will be all real numbers except negative 2 and positive 2. So it'll be all real numbers to the left of negative 2, negative infinity up to negative 2, not including it, round bracket. Union, all real numbers between negative 2 and positive 2, round brackets on each. Neither are included. And then union, all real numbers to the right of positive 2, not including it, round bracket up to positive infinity. That domain is all real numbers except negative 2 and positive 2. For part B, we want to determine if there is any symmetry. This is done by evaluating f of negative x and comparing it to the original function f of x. F of x is made up of, in the denominator, an even power of x, which will have y-axis or even symmetry. Subtracting a constant, which always has y-axis or even symmetry, since the two match, the entire denominator will have y-axis or even symmetry. In the numerator, we have an odd power of x, this is an implied first power, which will have origin or odd symmetry. Odd divided by even, since it's division and they do not match, the result will be odd. So f of x will have origin or odd symmetry. F of negative x is negative x divided by negative x squared minus 4, which is negative x divided by, a negative squared is positive, and then x squared minus 4. The negative in the numerator can move out front, so it'll be negative of x divided by x squared minus 4. Comparing this result to the original, it is exactly the same as the original, except it has a negative in front of it. So f of negative x equals negative f of x, which is the exact condition needed to have origin, also known as odd symmetry. This means that the graph will be its own mirror image over the y-axis followed by the x-axis. We will be sure that that is the case. For part C, we want to determine the y-intercept. This is the point where the graph crosses the y-axis, defined by x equals 0. We can find the corresponding y-coordinate by plugging the x-coordinate 0 back into the original function, y equals f of 0, which is going to be 0 over 0 squared minus 4, which is 0 over 0 squared is 0 minus 4 will be a negative 4. 0 divided by any non-zero number is 0. We have an x-coordinate 0. We find a corresponding y-coordinate also of 0. So 0, 0, the origin is the y-intercept. For part D, we want to determine any x-intercepts. These are the points where the graph crosses the x-axis, defined by y equals 0. Y, which is f of x, is going to be set equal to 0. Before we do this, we want to cancel any factors in the numerator with factors in the denominator for the original function. The numerator is an x. In the denominator, there's a factor of x plus 2 and a factor of x minus 2. There are no factors that can cancel. If there were, there are potential holes in the graph. After fully canceling out any factors from the numerator and denominator, we can now set y, which is f of x, equal to 0 and set it equal to just the numerator of f of x and solve for all x's. It's already solved for x since it's just an x in the numerator. We had a y-coordinate of 0. We found a corresponding x-coordinate also of 0. So 0, 0, the origin, is the only x-intercept here. For part E, we want to determine the vertical asymptotes. This is done by taking the denominator that's left over after canceling any factors from the denominator with the numerator. No factors canceled here. And setting the remaining denominator, x plus 2 times x minus 2, equal to 0 and solving for all x's. The factor of x plus 2 gives x equals negative 2, and the factor of x minus 2 gives x equals positive 2. These will be the two vertical asymptotes. We can now determine the behavior on each side of the vertical asymptote, starting with the x equals -2 vertical asymptote. We can determine the left side behavior by taking the limit as x approaches -2 from the left side. We will want to use the factored version of the function for this. So x over x plus 2 times x minus 2. Plugging a -2 in for each of the x's in the numerator will give a -2. In the denominator, for the first factor, -2 plus 2 is 0. But we're approaching -2 from the left side here, so we are more negative than -2. Added a 2, that will be a negative number. Yet it is approaching 0, so it'll be a -0. Plugging a -2 into the second factor, -2 minus 2 is a -4. In the numerator, we have a -2. In the denominator, negative times negative is positive. 0 times 4 is 0. A negative over a positive is a negative. Non-zero over 0 is an infinity. We can now determine the behavior on the right side of the x equals -2 vertical asymptote by taking the limit as x approaches -2 from the right side. Again, we use the factored version of the function. Plugging in x equals -2 in, we give a -2 in the numerator. For the first factor in the denominator, -2 plus 2 is 0. But we're approaching -2 from the right side here, so we are less negative than -2. When added a 2, that will be a positive number, though it is approaching 0, so it'll be a positive 0. Plugging a -2 into the second factor, -2 minus 2 is a -4. The numerator is a -2. The denominator, positive times negative is negative. 0 times 4 is 0. Negative over negative is positive. Non-zero over 0 is an infinity. We can now determine the behavior on the left side and right side of the x equals +2 vertical asymptote, starting with the left side by taking the limit as x approaches +2 from the left side. We'll want to use the fully factored version of the function here. Plugging a +2 in for each of the x's in the numerator, that will give a +2. In the denominator for the first factor, +2 plus 2 is a +4. For the second factor, +2 minus 2 is a 0. We're approaching 2 from the left side here, so we're less positive than 2. Subtracting 2 from that will be a negative number, though it is approaching 0, so it'll be a -0. So we have a +2 over a positive times a negative, which is a negative. 4 times 0 is 0. Positive over negative is negative. Non-zero over 0 is an infinity. And we can now determine the behavior on the right side by taking the limit as x approaches 2 from the right side. It's a fully factored version of the function. Plugging a +2 in for each of the x's in the numerator will give a +2. In the denominator for the first factor, 2 plus 2 will be a +4. For the second factor, 2 minus 2 will be a 0. But we're approaching 2 from the right side here, so we're more positive than 2. And subtracting 2 from that will be a positive number, so it's a positive number, yet it's approaching 0. It'll be a +0. In the numerator, we have a +2. In the denominator, positive times positive is positive. 4 times 0 is 0. We have positive over positive, which is positive. Non-zero over 0, which is infinity. For part F, we want to determine if there are any holes in the graph. These will occur if there are any factors in the numerator that cancel out fully with factors in the denominator. There are no factors that cancel here, so for holes there will be none. For part G, we want to determine the end behavior, horizontal asymptotes or slant asymptotes. F of x is a fraction, a quotient of two functions. In the numerator, there's a first power of x. In the denominator, the highest power of x is x to the 2. Since the power in the denominator is equal to or higher than the numerator, there will be a horizontal asymptote. Since the denominator is higher than the numerator, the horizontal asymptote will be y equals 0. The horizontal asymptote can be determined by setting y equal to the limit as x approaches positive or negative infinity. They will match here since f of x is a polynomial over a polynomial. And f of x, we do not want the factored version, the original, x over x squared minus 4 here. Plugging in the positive or negative infinity now will give the infinity over infinity indeterminate form. But we can divide the numerator and denominator by the highest power of x in the denominator. That will be x squared. Which will give limit as x approaches positive or negative infinity. In the numerator, we have x divided by x squared. In the denominator, we have x squared divided by x squared minus 4 divided by x squared. So we have the limit as x approaches positive or negative infinity. In the numerator, we can cancel one of the x's out, and that will leave behind a 1 over x. In the denominator, the first term, we can cancel both x squareds out. That'll leave a 1. For the second term in the denominator, there are no x's that will cancel. It will remain as a negative 4 over x squared. Each term that is a constant divided by x to a positive power will go to 0 as x approaches positive or negative infinity. The result of this is 0 over 1 minus 0, which is 0 over 1, 0 over any non-zero number equals 0. So the horizontal asymptote will be y equals 0. For part H, we want to determine the intervals of trend, relative maxima, relative minima, plateaus, and cliffs. All of this involves the first derivative, f prime of x. We will take this from f of x. We do not want to use the fully factored version. The original version will be the better version to use here. It is a quotient of two expressions of x, so we will need to make use of the quotient rule. This will require a little bit of room, so it can be worked out on another page. F of x equals x divided by x squared minus 4. The first derivative, f prime of x, will be the quotient rule. Derivative of the numerator, which is a 1, times the denominator left alone, x squared minus 4, minus the numerator left alone, x, times the derivative of the denominator, which is a 2x, and then the entire thing over the denominator squared. In the numerator, we can distribute the 1 into this expression. 1 times anything is that same thing, so it'll just be x squared minus 4. And we can multiply the negative x and the 2x, which will give a negative 2x squared. I'll have this over the denominator that we will leave alone. In the numerator, we can combine like terms together. 1x squared minus 2x squared will be a negative x squared. There is a minus 4 that doesn't combine with anything. And then over the denominator. We want to fully factor the first derivative. The numerator has a common factor of a negative 1. So the negatives, the ones implied, will factor out, which will leave behind a positive x squared and a positive 4. In the denominator, we have a difference of squares. X squared minus 4 factors into x plus 2 and x minus 2. The fact that the x squared minus 4 was squared means that each of these factors are squared. There's the version of the first derivative we're going to want. So it came out to the negative of x squared plus 4, and that entire thing divided by x plus 2 squared times x minus 2 squared. We have the first derivative written as a single fraction. All powers are positive, and it is fully factored, so we can now set the numerator equal to 0 and the denominator equal to 0 and solve for all x's. From the numerator, we have x squared plus 4 equals 0. We can solve for x by subtracting 4 from both sides. X squared equals negative 4. And then x will equal plus or minus the square root of -4, which is an even root of a negative number, which will be non-real numbers. From the denominator, which is already factored, the x plus 2 factor will give x equals -2, and the x minus 2 factor will give x equals +2. We'll now check to see which of these are in the domain. The domain is all real numbers except -2 and +2. So x equals plus or minus the square root of -4, which will be non-real numbers, are not in the domain. They're crossed out. They're not critical numbers. X equals -2 and x equals +2 are real numbers, but they are excluded from the domain. They were each found to be vertical asymptotes. And so they are also crossed out. They are not critical numbers. Therefore, we have no critical numbers. We can draw a domain line, a line representing the domain. It has no left end because it begins at -infinity, and no right end because it ends at +infinity. It does not include -2 or +2. -2 and +2 were found to be vertical asymptotes. They can be indicated on the domain line by putting dashed lines on them. So the domain is already split into 3 separate intervals. We can put any critical numbers on here to further split the intervals, but there are no critical numbers. So these are the intervals we will be testing on. We can pick a test value in each of the intervals. The first interval, -infinity to -2, we can pick -10. Next interval, -2 to +2, we can pick 0. Next interval, +2 to +infinity, we can pick +10. We can test the trend in each of the intervals by plugging these test values into the first derivative. We only care whether it is positive or negative, so we'll plug into the fully factored version, which is this one here. A couple of things about this. In the denominator, each factor is to an even power. Raised to an even power will always be positive, so that entire denominator is always positive, and it will not affect whether the first derivative is positive or negative. In the numerator, the x squared is always positive unless x is a 0, in which case it'll be a 0, but then it's added to 4, so it's always going to be positive for the x squared plus 4 portion, and that portion of it also will not affect whether the first derivative is positive or negative. The only thing left over is the negative in front of it all. What this means is that the first derivative will be negative for all test values. And therefore, no need to plug them in. Guaranteed, the first derivative will be negative, and we will have a trend decreasing in each of the intervals. We had no critical numbers here. X equals -2 and x equals +2 were vertical asymptotes. Since there were no critical numbers, we will have no relative maxima, relative minima, plateaus, or cliffs. There should be none of these on our graph. For part I, we want to determine the intervals of concavity and any inflection points. All of this involves the second derivative, f double prime of x. We'll take this from the first derivative. We do not want to use the fully factored version of the first derivative, and it will take a little bit of room to work out the second derivative, so it can be worked out on the other page. F double prime of x equals, we're going to take this from the first derivative. The best version to use is the version where all terms have been combined, but it has not been factored. That will be this one here. It is a quotient of two expressions of x, so the second derivative will also require the quotient rule. Derivative of the numerator, which is a -2x, times the denominator left alone, x squared minus 4 squared, minus the numerator left alone, -x squared minus 4, times the derivative of the denominator, which is a power rule, bring the 2 down, Leave the inside alone, x squared minus 4. Subtract 1 from the power, it'll now be to the first power, and then multiply by the derivative of the inside to complete the chain rule. And then this entire thing over the denominator squared. In the numerator, we'll leave the first term alone, negative 2x, and then x squared minus 4 squared. For the second term, we can collect the constants together. There's a 2, and out front there's an implied negative 1. 2 times 2 is 4, times that negative 1 will be a negative 4. Everything's multiplied here, so we can multiply in any order. Negative 4. There is an x. There is a negative x squared minus 4. And there is a positive x squared minus 4. All of this is divided by x squared minus 4 squared and then squared again. If we raise and raise again, in this case we multiply the exponents. 2 times 2 is 4. Now, as a rule of thumb, the power in the denominator should only increase by 1 after taking a successive derivative. Comparing the power in the denominator in the second derivative to the power in the denominator of the first derivative, it's increased by what looks like 2 here. But that's because in the numerator, we have a common factor of a power of x squared minus 4 that we'll be able to factor out. And once it factors out, it will be able to cancel down with the denominator to reduce that power. That'll be part of what we need to do here. We want to fully factor the second derivative. There is a common factor from the constants in front of each, negative 2 and negative 4. We can factor out a negative 2. There's an x in each, so we can factor out an x. And there is a power of x squared minus 4 in each. The first term has a power of 2. The second term has a power of 1. We can factor out the lower of the two powers, which will be the power of 1. Factoring all of this out, we'll leave behind. Taking out the negative 2. This will become a positive, and it will become a 1. This will become a positive, and it will become a 2. Factoring out the x's will disappear. And factoring out an x squared minus 4 to the first power. Factoring is division. Division is subtraction of exponents, so we will subtract a power of 1 from this. 2 minus 1 will become 1. And from this is an implied first power. Subtracting 1 from it will become a 0, and anything raised to 0 is a 1. There's what's left over. We have a positive implied 1 times x squared minus 4 to the first power, and then plus 2 times a negative x squared minus 4. So what was left over was an implied positive 1, which we don't need to write, times an x squared minus 4, and then a plus 2 times a negative x squared minus 4. All of this is divided by x squared minus 4 to the fourth power. Now we can cancel the factor that we brought out. It was to the first power. With one of the powers in the denominator, it will leave behind 3 powers. Now it is 1 pi power higher than what it was in the first derivative, as it should be. So f double prime of x equals negative 2x. Inside of the square brackets, we can distribute the implied positive 1 in here, which will leave x squared minus 4. And we can distribute the positive 2 in here, which will be a negative 2x squared minus 8. All of this is over x squared minus 4, which is now cubed. So we have a negative 2x. We can combine like terms together inside of the square brackets and turn them into parentheses. X squared minus 2x squared will be a negative x squared. Minus 4 minus 8 will be a negative 12. All over x squared minus 4 quantity cubed. We want to fully factor the second derivative. In the numerator, there is a common factor of a negative 1 inside of the parentheses. It can factor out. It will multiply with the negative 2 to become a positive 2. There's an x already. And factoring out that negative 1 will leave behind a positive x squared and a positive 12. In the denominator, we again have a difference of squares. It will factor into an x plus 2 and an x minus 2. This time the power on it is 3, so each of these will be to the power of 3. There's the version of the second derivative we're going to want. This does not factor any further because it's a sum of squares, so we leave it as is. So this equals a positive 2x times x squared plus 12 divided by x plus 2 cubed and then x minus 2 cubed. So we have the second derivative written as a single fraction. All powers are positive, and it is fully factored. We can now set the numerator equal to 0 and the denominator equal to 0 and solve for all x's. From the numerator, we have a factor of x that will give x equals 0. We also have a factor of x squared plus 12. That'll give x squared plus 12 equals 0. We can solve for x by subtracting 12 from both sides, so x squared equals negative 12. And then taking the square root of both sides, x will equal plus or minus the square root of negative 12. Once again, we have a negative under an even root, and that will be non-real numbers. From the denominator, which is already factored, the x plus 2 factor will give x equals negative 2, and the x minus 2 factor will give x equals positive 2. We'll now check to see which of these 4 different sets of values, this one has 2, so technically 5 values altogether, are in the domain. The domain is all real numbers except for negative 2 and positive 2. X equals 0 is a real number, and it is in that domain. So we do keep that. It is a candidate number. X equals positive or negative the square root of negative 12. An even root of a negative number will be a non-real number, which cannot be in the domain. The domain is all real numbers except negative 2 and positive 2. So we cross these out. They are not candidate numbers. X equals negative 2 and x equals positive 2 are real numbers, but they are excluded from the domain as they were found to be vertical asymptotes. So we can cross them out. They also will not be candidate numbers. So we only have one candidate number, x equals 0. We can now draw a domain line, a line representing the domain. It has no left end because it begins at negative infinity, and no right end because it ends at positive infinity. The domain does not include negative 2 and positive 2. They are vertical asymptotes. We can indicate that by dashed line on each. We can now put all candidate numbers on here in order. We only found one candidate number, x equals 0, which will be between negative 2 and positive 2. This splits the domain, which was already in 3 intervals, into what is now 4 separate intervals. We can pick a test value in each of the intervals. The first interval, negative infinity to negative 2, we can pick negative 10. The next interval, negative 2 to 0, we can pick negative 1. The next interval, 0 to positive 2, we can pick positive 1. And then the last interval, 2 to positive infinity, we can pick positive 10. We can test the concavity by plugging these test values into the second derivative. We only care whether it is positive or negative, so the best place to plug in is the fully factored version. That's this. A couple of things about this. The 2 in the numerator is always positive, so it will not affect whether the second derivative is positive or negative. X squared is always positive unless x is 0, but then it's added to 12, and that's guaranteed always positive. So that portion of it is also always positive and does not affect whether the second derivative is positive or negative. The x is to the first power, so it will, and in the denominator these are each odd powers, which can be positive or negative. So they will matter. Odd powers always matter. The portion of the second derivative that matters, therefore, is this. Plugging in the negative 10 in the denominator, negative 10 plus 2 is negative, cubed is negative. Negative 10 minus 2 is negative, cubed again is negative. Negative times negative is positive. In the numerator, plugging in negative 10, we have a negative over what is a positive, which overall gives a negative second derivative, and this corresponds to concave down. Plugging negative 1 into the portion of the second derivative that matters, we have in the denominator negative 1 plus 2, which is positive, cubed will be positive. Negative 1 minus 2, which is negative, cubed will be negative. Positive times negative is negative. In the numerator, we have a negative 1. And so we have a negative over a negative, which is a positive second derivative, and this corresponds to concave up. Plug in the test value of positive 1 into the portion of the second derivative that matters. 1 plus 2 is positive, cubed will be positive. 1 minus 2 is negative, cubed will be negative. Positive times negative is negative. In the numerator, we have a positive 1. Positive over negative is negative. We have a negative second derivative. This corresponds to concave down. Plugging a test value of positive 10 into the portion of the second derivative that matters. 10 plus 2 is positive, cubed is positive. 10 minus 2 is positive, cubed is positive. Positive times positive is positive. In the numerator, we'll have a positive 10. Positive over positive is positive. We have a positive second derivative. This corresponds to concave up. We have only one candidate number here. Right at the candidate number of x equals 0, we do have the concavity changing from concave up to concave down. So x equals 0 will be an inflection point. It has an x-coordinate of 0, and it has a corresponding y-coordinate that can be found by plugging the x-coordinate back into the original function. So y equals f of 0, which is 0 over 0 squared minus 4, which is 0 over 0 squared is 0 minus 4 is a negative 4, and 0 over any non-zero number is 0. So we have a corresponding y-coordinate of 0. 0, 0. We found that to be the y-intercept and the only x-intercept up above. Apparently it's also an inflection point. X equals negative 2 and x equals positive 2. Even though the concavity did change around each of those are not candidate numbers. They are not part of the domain. They're actually vertical asymptotes. We can now draw a graph. We have a vertical axis. We have a horizontal axis. We have the domain is all real numbers except for negative 2 and positive 2. And that's because we found x equals negative 2 and x equals positive 2 to be vertical asymptotes. So we can put those on the graph. X equals negative 2 will be somewhere about right here. And x equals positive 2 will be the same distance away, but on the other side. So we can label these. We have this one is a negative 2. one is a positive 2. We found that we will have origin or odd symmetry. This means the graph will be its own mirror image over the y-axis followed by the x-axis. We'll be sure that that is the case. For the y-intercept, we found the origin 0, 0. So it's going to pass through 0, 0, the origin. We can label this. We found the only x-intercept to also be the origin, so it should not cross the x-axis anywhere else. We have the vertical asymptotes, and we have determined the behavior on each side. Starting with the x equals -2, on the left side, we found that its behavior is to approach negative infinity. That means on the left side, it will be headed down here. On the right side of the -2, we found the behavior to be positive infinity. So on the right side, it's headed up here. For the x equals +2 vertical asymptote, on the left side, we found that its behavior is towards negative infinity, so it will be down here. And on the right side, its behavior is to positive infinity, so it will be up here. There are no holes in the graph. We found the horizontal asymptote to be y equals 0, which is the x-axis. So we can put a dashed line along the x-axis, and we will be sure on the left and right ends to approach to that horizontal asymptote. We found in each of the intervals that it should always be decreasing, and there should be no relative maxima, minima, no plateaus, no cliffs. So be sure that we stay decreasing in each of the intervals. We did find an inflection point at 0, 0. And on the left side of it, it should be concave up, and on the right side of it, it should be concave down. But that inflection point was not found to be a plateau. We have no plateaus, which means that it will not go to a horizontal tangent like a plateau. It'll pass through in a diagonal fashion, and then we'll have a diagonal type of inflection point. On the left side, it should be concave up. Now, it should be diagonal here, so it should be concave up here, kind of like this, and then passing through in a diagonal fashion, and then it should change over to concave down on the other side of it, so like so, and passing through in a diagonal fashion, like so. So on the left side of the vertical asymptote of x equals -2, we should have decreasing concave down, and it should follow that it's going to be approaching the horizontal asymptote of y equals 0 on the left and going to negative infinity on the left side of the x equals -2 vertical asymptote. So it should stay decreasing and concave down during this time. There's only one option for that to do that, and it means it's going to decrease and be concave down like so. Between -2 and +2 vertical asymptotes, we have decreasing. It should be concave up on the left of 0 and concave down on the right of 0. So that means that it will look something like so. And it has the behaviors on each side of the vertical asymptotes as it should. And then on the right side of the x equals +2 vertical asymptote, we should have a decreasing concave up, and it should once again go towards the y equals 0 horizontal asymptote, while decreasing and staying concave up. And that means it will have behavior like so. So we have a domain of all real numbers except -2 and +2. They are vertical asymptotes. We are showing the origin odd symmetry. That means that the mirror image of the graph over the y-axis and then over the x-axis will overlap with itself. This piece here, if we take the mirror image over the y-axis, will end up over here. And if we take the mirror image over the x-axis, this will end up down here. And it lines up with itself. This piece, taking the mirror image over the y-axis, will end up here, and then taking that over the x-axis will end up here, and it will line up with itself as well. So it's showing the origin or odd symmetry. It's its own mirror image over the y-axis followed by the x-axis. We have all behaviors around the vertical asymptotes being followed. We have the horizontal asymptote being followed. Everything is being followed here. It is decreasing in all intervals as it should be. So this will be the graph of f of x.